Hi, welcome to the Olympiad geometry. Let's continue our study on geometry treasure. In last video, we talked about the meaningless theorem, the generalization of the meaningless theorem, and the second angle form of the meaningless theorem. In this video, let's continue to the Ceva theorem. First, we talk about the second angle form. Let A prime, B prime, C prime be the points on the lines of the edges of the triangle ABC. O is a point not on these lines. Then AA prime, BB prime, CC prime are in parallel or concurrent if and only if this is valid, right? So let's just review the Ceva theorem shortly, and then we come back to this one. This is a triangle ABC, and we have A prime, B prime, C prime on each edge. We say that if AA prime, BB prime, CC prime are in parallel or concurrent, then we have AC prime to C prime B times BA prime to A prime C times CB prime to B prime A equals to 1, right? That's a Ceva theorem. And the angle form would be sine angle BA prime to sine angle A prime AC times sine angle CB B prime to sine angle B prime B A times sine angle AC C prime to sine angle C prime C B equals to 1, right? That is the angle form of the Ceva theorem. And now we are looking at the second angle forms of the Ceva theorem, which is that we have another point out of the triangle ABC. We call it O. Well, it's not necessary to be out, right? It's just not on the three lines. And then we connect AO, BO, B prime O, A prime O, and C prime O, and CO, right? So basically, it's just the same as what we proved in the meaningless theorem. Basically, we just transfer each edge ratio to this angle ratio, right? So you can see eventually we transfer the BA prime to A prime C to the angle ratio, which is angle BOA prime to A prime OC, right? So we transfer it to the area ratio, and then all the edge, production of the edge and the ratio of the edge, they all cancel each other. So we only have the sine angle of these angles. So that is obvious, okay? Now we look at the theorem. Theorem is saying that if DEF are points on BC, CA, AB in triangle ABC respectively, so right, we have triangle ABC here, and we have DEF on each edge, and we know that AF to FB equals to lambda 1, BD to DC equals to lambda 2, CE to EA equals to lambda 3. And we know that these three ADB, CF, these three segments form a triangle, right? We call this triangle as PQR. Then we want to calculate the area ratio of the triangle PQR to the area of triangle ABC. Right, we want to do this. So just look at this figure. We know that the triangle ABC equals to the area of triangle PQR plus the area of triangle ABQ plus the area of triangle BCR plus the area of triangle APC, right? Triangle ABC equals to this one plus this one plus this one plus this one. Okay, so how can we calculate the area ratio of, that means the area of PQR to ABC equals to 1 minus the area of ABQ, triangle ABQ to ABC, minus the area of triangle BCR to ABC, minus the area of triangle APC to ABC, right? So let's think about this one. How can we calculate the area of triangle ABQ to the area of triangle ABC? ABQ to ABC equals to the area of triangle ABQ to the area of triangle ABE times the area of triangle ABE to the area of triangle ABC, which equals to BQ to BE times BE to, well, not BE, right? The area of triangle ABE to the area of triangle ABC, so it's AE to AC. Right, we already know AE to, we know CE to EA equals to lambda 3. So we know AE to AC equals to 1 divided by 1 plus lambda 3, right? But we don't know the ratio of the PQ to QE. However, we can calculate it based on the Menelaus theorem. So we use the Menelaus theorem for the triangle BCE and the intersection line DQA, right? We can have BD to DC times CA to AE times EQ to QB equals to 1, right? Which means BD to DC, that is lambda 2, times CA to AE, CA to AE, which is 1 plus lambda 3, right? That is QB to EQ, right? That is QB to EQ. Lambda 2 times 1 plus lambda 3. So based on this, we know that we want to calculate for BQ to BE, which is BQ to BQ plus QE, right? BQ plus QE. So we know that BQ to BE equals to lambda 2, 1 plus lambda 3, 2, 1 plus lambda 2, 1 plus lambda 3, right? That's BQ to BE. And that is saying we know the BQ to BE and we know the AE to AC, AE to AC, which is 1, 2, because CE to AE is lambda 3, so AE to AC is 1 to 1 plus lambda 3, right? So we get the area of triangle ABQ to the area of triangle ABC equals 2. Lambda 2, 1 plus lambda 3, 2, 1 plus lambda 2 plus lambda 2 lambda 3 times 1, 2, 1 plus lambda 3, which equals 2. Lambda 2 divided by 1 plus lambda 2 plus lambda 2 lambda 3. Right? Okay, based on this, we know that for the other two triangle divided by the other two triangle area to the triangle ABC area ratio would be lambda 1 to 1 plus lambda 1 plus lambda 1 lambda 2, and another one would be lambda 3 to 1 plus lambda 3 plus lambda 3 lambda 1, right? So now we can calculate for the area of triangle PQR to the area of triangle ABC, which equals to 1 minus lambda 1 to 1 plus lambda 1 plus lambda 1 lambda 2 minus lambda 2 to 1 plus lambda 2 plus lambda 2 lambda 3 minus lambda 3 to 1 plus lambda 3 plus lambda 3 lambda 1, right? And it equals 2. So the denominator would be 1 plus lambda 1 plus lambda 1 lambda 2 times this one, right? Denominator would be this for sure. So let's just consider about the denominator, which is 1 plus lambda 1 plus lambda 1 lambda 2, 1 plus lambda 2 plus lambda 2 lambda 3, 1 plus lambda 3 plus lambda 3 lambda 1 minus lambda 1, 1 plus lambda 2 lambda plus lambda 2 lambda 3 minus lambda 2, 1 plus, well, I have another term, sorry. Let me rewrite this part. So minus part, okay? Minus lambda 1 times the other 2, which is 1 plus lambda 2 plus lambda 2 lambda 3, and 1 plus lambda 3 plus lambda 3 lambda 1, right? And minus lambda 2 times 1 plus lambda 1 plus lambda 1 lambda 2 times 1 plus lambda 3 plus lambda 3 lambda 1, right? And then minus lambda 3 times 1 plus lambda 1 plus lambda 1 lambda 2, 1 plus lambda 2 lambda plus lambda 2 lambda 3. Okay, I'll move this forward when we calculate this. So it equals 2. Think about this one. We have this term, and this term, they are same, right? So lambda 1 minus, and we have 1 plus lambda 1 lambda 2 times 1 plus lambda 2 plus lambda 2 lambda 3, 1 plus lambda 3 plus lambda 3 lambda 1. That's for the combination of these two, right? And then we think about how can we combine this one and this one, right? So for this one and this one, they have the same factor form of this one, right? So we can leave it there. Then we have 1 plus lambda 3 plus lambda 3 lambda 1. And for the first term would be, I'll just extend this one. So 1 plus lambda 2 plus lambda 2 lambda 3 plus lambda 1 lambda 2 plus lambda 1 lambda 2 square plus lambda 1 lambda 2 square lambda 3, right? And then for here we minus lambda 2 minus lambda 1 lambda 2 minus lambda 1 lambda 2 square. That's it, right? That's for the first three terms. And then what we can have here is that we have 1 left and lambda 2 cancel, lambda 2 lambda 3 left, and lambda 1 lambda 2 cancel, lambda 1, lambda 2 square, cancel. And this one, we keep it. So we have 1 plus lambda 3 plus lambda 3 lambda 1 times 1 plus lambda 2 lambda 3 plus this one, which is lambda 1 lambda 2 square lambda 3. Right? And then we use this one minus lambda 3, 1 plus lambda 1 plus lambda 1 lambda 2, 1 plus lambda 2 plus lambda 2 lambda 3. Okay, so now it's difficult to tell whether how to do the factor of this one, so we just extend it and do the calculation, right? So bear with me. We have 1 plus lambda 2 lambda 3 plus lambda 1 lambda 2 square lambda 3 plus lambda 3 plus lambda 2 lambda 3 square plus lambda 1 lambda 2 square lambda 3 square plus lambda 3 lambda 1 plus lambda 1 lambda 2 lambda 3 square plus lambda 1 lambda 1 square lambda 2 square lambda 3 square, right? And then we minus the first term would be lambda 3, right? Because this one, and the second term would be lambda 2 lambda 3, right? Because this one, and then minus lambda 2 lambda 3 square, right? That's for this one. And let me continue here. We minus lambda 1. So lambda 1 lambda 3 minus lambda 1 lambda 2 lambda 3 minus lambda this one times this one times this one. So lambda 1 lambda 2 lambda 3 square minus this one. So lambda 1 lambda 2 lambda 3 and minus lambda 1 lambda 2 square lambda 3 minus lambda 1 lambda 2 square lambda 3 square. Okay, so that's all we have. And now we look at what we can cancel. We have lambda 3 lambda 1 here. We have this one, so we cancel. And we have lambda 3 here. We have lambda 3 here. Do we have lambda 2 lambda 3? Yes, we have it here. And do we have lambda 2 lambda 3 square? Yes, we have it here. And what about lambda 1 lambda 2 lambda 3? We don't have it, so we have twice of it. And what about lambda 1 lambda 2 lambda 3 square? Yes, we have it here. What about lambda 1 lambda 2 square lambda 3? Yes, we have it here. And what about lambda 1 lambda 2 square lambda 3 square? Yes, we have it here. So what we left? This one, and 2 of this one. So we have 1 minus 2 lambda 1 lambda 2 lambda 3 plus lambda 1 square lambda 2 square lambda 3 square, which equals to 1 minus lambda 1 lambda 2 lambda 3 square. Okay, so we just proved that the denominator is what we just get, and the denominator is production of these three terms, right? Okay, we just prove it. And the conclusion is that based on the above setting, if AF to FB equals to BD to DC equals to CE to E equals to lambda, then we have this one. It is obvious, right? Because if they are the same, then on the Denominator is this one. Well, I write it as lambda 3. It's lambda. And on the denominator, it's 1 plus lambda square to the power 3, right? So this one can be rewritten as lambda minus 1 plus lambda square, right? So we have square here, and we have 1 plus lambda square to the power 3. Then we cancel 2 of them. That's what we left, right? Okay, so in this video we shortly review the Ceva theorem, and we extend it for the second angle form and also calculate for the area around it. Okay, I hope you like this video. See you in next one. If you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. Thank you.